And we've finally made it to some equations where we've got to find out what the variable actually means, but we still need a common denominator. We can do this the same way we've done the previous examples where we look at all the factors. For example, there's 6's in both of these, but there's not a 6 in the first numerator or the first denominator. So we're going to multiply that one by 6, which means we need to multiply the denominator as well. And then you can look at the other factors in the denominator. They both have a squareds, but this one only has an a. It doesn't have the a squared. So how do we make it a squared? Well, we need to multiply it by a. And when we do that, we end up with 6 over 6a squared equals a over 6a squared plus 1 over 6a squared. Now all the denominators are 6a squareds, right? So if I were to multiply everything by 6a squared, you don't necessarily have to write this, just understand that it's happening. Then 6a squared over 6a squared, they all divide out. So mathematically that's okay, or that's a correct thing that we can do to maintain equality because we're doing it to every term. At the very beginning, we have to multiply. If I only want to multiply one term, then I have to multiply it by something over itself because that's 1. But if I multiply everything, I don't have to multiply it by something equal to 1. So for example, if I have x equals 2, if I decide to multiply both of those things by 2, then I get 2x equals 4, which is still the same, has the same measure of equality, that x, if you plug in the original, x equals 2, it's still a true statement, as long as we do it to everything. So in the beginning, we're multiplying things by 1, so that we can just multiply one term. And then when we multiply every term by 6a squared, the denominators all cancel out. So eventually people just mark out those denominators once they're the same, but I want you to understand why they're doing it from a standpoint of equality. You get a equals 5. Okay. On these, it says to be careful or wary of extraneous solutions, which would just be a solution that, going back to excluded values, if you have an excluded value, for example, this one, we see that a cannot be 0. And when we solve, we get a equals 5. We don't get a equals 0. So it's not a problem. If we had done all of the algebra, we got that a equals 0, then that would be an extraneous solution. It would be, we know a can't be 0, even though the math is telling us that's what it should be. It happens, and that's why you just need to at least be conscious of that possibility. Okay, now let's look at the next one. Okay. Number 34 could be pretty complicated if you don't factor first. Just like a lot of things, you want to look at the pieces before you get a little too crazy and multiply by stuff you don't have to multiply by. So we've got a squared plus 5a. That has a greatest common factor. Greatest common factor is a. And when we do that, we see that both of these first denominators can be factored into a times a plus 5. And why is that significant? Because we see that all of those denominators have an a plus 5 as a factor in their denominators. The only other factor is the first two denominators have a's in them. The last one doesn't. So we're going to multiply it by a so that it now has the same denominator. We have to multiply the numerator as well. We get 6 equals 1 plus a. Subtract 1 from both sides. Also, so once the denominators are the same, I canceled them out and only looked at the numerators. And I get a equals 5. And that is not an excluded value. From this factor, a couldn't be 0. And from this factor, a couldn't be negative 5. But it was neither of those things. So I don't have an extraneous solution. I have a real solution. All right. Now let's look at 36. With 36, you want to, again, factor any denominator that you can. So I have a greatest common factor in this middle denominator, 2 times x plus 4. And then we see that both of these denominators have 2's in them. So I'm going to multiply this one. You're like, well, this one doesn't even have a denominator. Well, sure it does. It's a 1. That's why we don't write it. But now we're going to make it into a 2. We'll multiply by 2, which means we multiply the numerator as well. So let's do I'm doing a middle step here. 1 over 2 equals x plus 1 over 2 times x plus 4 plus 6 over 2. If that looks unnecessarily complicated, it kind of is, but it's a middle step. So we have all these denominators of 2. You could combine the 6 over 2 and the 1 over 2 at this point if you wanted, but we'll just leave it. So the middle term has an x plus 4 in its denominator, but the first term doesn't. So we're going to multiply it by x plus 4 over x plus 4. And we're going to do the same to the last one. So now I recognize that my denominators are all the same, so I'm going to cross them out and multiply out all my numerators. X plus 4 equals x plus 1 plus, now let plus 6 times x plus 4. Got x plus 4 equals x plus 1 plus 6x plus 24. That's a 4, obviously. So this is 7x plus 25 equals x plus 4. Subtract 4 from both sides to get rid of this 4. I'll do that back up here. And this is going to become 21, 25 minus 4. And then I'm also going to subtract 7x from both sides. This becomes negative 6x. Divide by negative 6, negative x equals negative 7 over 2. Let's do, we're going to do 37 and 38 because there's two main types of problems here. So this is an extension of the concept of rational equations. And this is a type of problem that could be used, or you could use rational equations to solve. So let's say that Cody can pick 40 bushels of apples in 9 hours. Arjun can pick, or Arjun, I don't know, can pick the same amount in 10 hours. Find out how long it would take them if they work together. So let's say these two guys both work in the same industry and they know how fast they pick apples together. And they have a job that they have to do, but they can work together this time. And so somebody at home is like, hey, tell me when you're going to get home. Like, well, I don't know. Cody's pretty fast bushel of apple picker. And I'm not quite as fast, but I'm decent. And so I don't know how long it'll take us. Well, using this formula, you could give a reasonable guess. So we turn it into a rate or a speed for Cody and for Arjun. We've got 40 bushels in 9 hours. So that's bushels per hour if you were to divide it out. And this would be 40 divided by 10 for Arjun. That's bushels per hour again equals. So if they had the same amount of bushels, then what would their time be? How long would it take them? And we talked about how just like the other ones where we had common denominators and we multiplied everything to get rid of the denominators, if we divide all these things by 40, okay, we can do that mathematically. If we divide one thing, we divide all things, and these would all cancel out and become ones. So even if you're talking about 40 bushels of apples, it's still one job. They can do the job, the 40 bushels of apple job in 9 hours, and one 40 bushel set in 10 hours. So this just becomes 1 over 9 plus 1 over 10 equals 1 over x. And you don't have to show this every time. And what do we do from there? Well, you can think of it as we did before. There's multiple ways to think about these things. You can do it like we did the rational equations, because this is one. And you can think common denominators, or you can think like, how would I get rid of a 9 in the denominator? Well, I'd multiply by 9. We talked about the last problem is that you can't just multiply the numerator of one term. You have to multiply all the terms. And so mathematically, we can maintain equality by doing that, but these 9s cancel out. So you end up with 1 plus 9 over 10 plus 9 over x. And then we're going to do the same thing with the 10. I want to get rid of that 10, so I'm going to multiply by 10. Well, when I do that, I have to multiply everything. Move this over here. 1 times 10 is 10 plus, now this is not 90 because 10 divided by 10 is 1. So let's simplify that and make it 9 equals 90 over x. See, this 10 doesn't have a 10 below it to cancel it out, so we multiply. You can make that into 19 equals 90 over x. And now we need to multiply by x. So like one last multiplication, these cancel out, you get 90 equals 19x. Divide by 19, you don't need me to do that, I've got a calculator for it, but that's the amount of hours. 90 divided by 19 is the amount of hours it would take them to work together. Now 38, last one for this video. Sometimes we know how long it would take them to do it together, but maybe Mike has never done this by himself, so he doesn't know how long it would take him by himself, and he wants to figure that out. So what are they doing? They are tarring a roof. Okay, let's assume all the roofs are the same size. So it says together they can do this in 6 hours. So Bill can do it by himself in 10. So one roof in 10 hours. So that's 1/10 of a roof every hour for Bill. Plus one roof in, we don't know how many hours for Mike, equals one roof in 6 hours for the both of them. So now we multiply by 10 everywhere. These 10s cancel out. We get 1 equals 10. No, 1 plus 10 over x equals 10 over 6. There's some simplifying we could do here, but we will skip that. Multiply by 6. 10 equals 60 over x plus 6. And now I'm going to multiply by x everywhere. Those will cancel out. And I get 6x. I want that to be an equal sign really bad. Equal or plus 60 equals 10x. Subtract 6x from both sides. When you're solving for a variable, you want all the variables on the same side. Divide by 4. And we find out that old Mike isn't the fastest in the world at tarring the roof, but he can do it in about 15 hours. Almost done with part 1.